Alright, so this electrostatics review question is really about practicing how to calculate forces, fields, and potentials and some of the similarities and differences. And sort of remembering the difference between calculating the magnitude of the equations on the sheet and remembering the directions based on kind of your knowledge of physics and how charges interact. So we have I'm going to put that off to the side, I think. So we have a coordinate grid. So our y direction and our x direction. There's three charges at it, and they're all kind of fixed in place. And we want to see sort of what forces happen where. So we have two charges that are sort of symmetric on the y-axis, and then another charge a little bit farther out in the x-axis. So this point is negative a, this point is positive a, and this point is 2a. And we're told that the red charges are negative 2q, where q is just any arbitrary unit of charge, and the blue charge is plus, or not plus, it's a minus as well, but only 1q, so minus q. So the first thing we need to do is we need to figure out the magnitude of the net force on the blue charge, the negative 1q charge, due to the other two. And we know that forces can be added, but as vectors, right? So since these are negative charges, all of them, the force will repel. So the blue charge is going to get pushed away. So we have one force, it's going to be kind of like that, right, directly radially away from the bottom charge, and the other one is going to be directly radially away from the positive charge. And those vectors are going to be equal length because the charges are equidistant away and equal charge magnitude. So now we're ready to actually start kind of computing things. We know a little bit of what's going on. So we want the net force. So I'm going to call this one 1 and that one 2 to kind of distinguish them. So it's the force due to 1 plus the force due to 2. And you notice I've got the vector notation there because we have to vector sum them. And we know what the force due to a point charge is, right? We have the equation sheet. It's K Q Q, or Q1 Q2 over R squared. And we've already drawn the direction, so we've got kind of that considered. We have to do a little bit more, but that's at least the magnitude part. So the first thing we notice is in looking at these arrows, again, if they were exactly equal length, if I draw the x and the y components for each, I see that the y components are equal magnitude in exactly the opposite direction. Right, so the y components cancel. But the x components are the same magnitude in the same direction. So the x components are the same. So F1 plus F2 is actually just 2 times the x component, which is that cosine theta thing. Okay, and we'll figure out what cosine theta is in a second, but right, that's that angle. That would give us the x component. So now we can actually figure out this a little bit more easily. We need to figure out what r is. So r is this exact path between them. We can use the Pythagorean theorem to find r. So r squared is a squared, the vertical part, plus the quantity 2a squared, or 5a squared. Right? And now we just need to figure out this theta, but we can, well, specifically cosine theta, but we can see because this is all one sort of straight line, this angle theta and that angle theta have to be the same. So we can write from that cosine theta is the adjacent side, or 2a, over the over the hypotenuse, which we just found is that 5a squared, or sorry, square root of 5, and then a, right? Take the square root of 5a squared. Right, so cosine theta, right, the a's cancel, is 2 over root 5. So now we can plug all this stuff in. So 2k, one of the charges is charge negative 2q, the other charge is negative q. We have an r squared, that's 5a squared, and we have a cosine theta, which is 2 over root 5. That's still kind of sloppy. There. Right? I'll clean that one up too. Okay, so now we just need to multiply things together. So we have a 2, let's get some colors. So we have a 2 and a 2 and a 2. So we multiply all those, we get an 8. In the denominator we have 5 and the square root of 5, so we'll just leave that alone. And we have a q squared in the numerator, and an a squared in the denominator. That's still terrible. There. Right? And so this is the final answer, right? Our answers in terms of q and a and fundamental constants, because I forgot to write that k in there. So right, k is the 1 over 4 pi epsilon naught fundamental constant. So that one's fine too. So this is our final answer. You notice we had to do a lot with vectors and vector components and remembering how to do vector sums. And it was kind of a pain, which is sort of typical of the force. It's not usually all that fun to try and calculate. All right, so part B, now we have to figure out the electric field, which is a lot like the force, but not exactly. So I'm going to redraw the coordinate system, starting over again with a nice fresh one, because we're trying to find the electric potential at the origin, not at one location of the charge. Actually, I'm going to move that one a little bit farther out. And so again, this is A, or negative A, this is A, and this is 2A. Right? Actually, that blue charge could be a bit bigger. And charges are still the same magnitude, so the blue is the plus or minus 1q, and the red is the minus 2q's. Okay, so the electric field is again a vector sum, and here actually I should indicate, well, we care about the electric field at the origin. So the electric field is the sum of the electric field due to the first, the electric field due to the second, and the electric field due to the third charge. Right? So it's a vector sum again, but this one actually we're going to find is a little bit easier, because we write the in general statement of what the electric field of point charge is. That is kq over r squared. And this is a magnitude, once again. The electric field is defined to point in the direction towards a negative charge or away from a positive charge. So, this, oops, I forgot a subscript on one of these, so there's 2. So if we give our charges all their names, right, 1, 2, and 3, now we can start drawing sort of what these vectors have to be. I'm going to use orange for all of them. So all these charges are negative, so the fields are at the points are going to point towards the charges. So for point 1, or for charge 1, the field is going to point that way. For charge 2, it's going to point that way, and for charge 3, it's going to point that way. I haven't tried to draw the magnitudes a whole lot, but I've drawn the directions correctly. And you should notice something very, very quickly, given this calculation and the arrows for for fields 1 and 2. Charges 1 and 2 are the same q, right? Same q, and they're the same distance from the point. So the magnitudes of them are the same, and the arrows we drew are exactly the opposite direction. So the vector sum of fields 1 and 2 is 0. So all we care about is the third, the negative 1q charge, a distance 2a away. Right? And so now we just need to plug in that to the formula. Right? Again, we only care about the magnitude as well, so we're just going to do this. And so this is k negative q, and r is the distance from the charge to the origin, which is 2a squared. Oops, not squared there. So we take the magnitude of that, so that cancels the negative sign, or well, not cancels it, it gets rid of it. So we have kq over 4a squared. Right, and that'll be the electric field at the origin. And the direction is sort of what, it's the arrow that's left over, right? It's this one, so it's to the right. And I realized actually I should go back to the previous one. I've kind of already said it, but just to make sure, the direction of the force, well, we showed this statement, right? The y components cancel, only x components are left. So the net force is in this sort of away from the origin direction, only the x component, and away because it's repulsive. Okay, so back to field. So we've got the direction, we've got the magnitude, we're done with part B. Finally, we have to do the same sort of process for the electric potential. So we put our charges in place. And label where they're at. Okay, so the electric potential is nice because the electric potential is not a vector. It's still a sum, so the electric potential is V1 plus V2 plus V3. But you notice it's not a vector sum. So this is a lot easier to compute. And we know that the electric potential for a point charge is KQ, so I'll keep writing capitals, KQ over R. And we want the value at the origin. So we just have to write it down for each of them. And it's just a number, which makes our life easy. So for charge 1, K negative 2Q, and the distance is, well, actually, it's not negative, it's A, right? So the distance A from the origin. We add to that the result for charge number 2, which is the same magnitude and the same distance. And then finally we have to add the same thing for charge number 3, which is only a negative Q, and it's a distance 2A away. And so now we just combine all that. Every term has a K and a Q and an A. So we factor those out. We get a negative 2, a negative 2, and a negative 1/2. So we combine all those together, and we get a negative 9KQ over 2A. So a negative 9/2, right? And that's it. We're done, right? There's no direction, there's no components, there's no anything. The electric potential is significantly easier than the others. So if you got stuck or frustrated with the force and field part, always look for potential because it's a lot easier. All right, so this last part, it's only a sketch, but this one can be kind of tricky. So I'm going to talk about it a bit. So our x direction and our y direction, or actually, hang on. Our x direction and this axis is the force that the charge feels. So what we're going to do is we're going to move our charge, the negative 2 charge, along the x-axis from really far off in the negative direction all the way to really far off in the positive direction. We want to see sort of what force it feels. And we know that we have negative charges sitting sort of above and below the origin. And we've done a little bit of work in parts A and B relating to calculating the force and field at various points. So the first thing we note is from part B, we are told that the electric field at the origin is only due to the charge negative Q. that means that if we don't care about the electric field created by that charge, because it can't feel its own field, then the electric field at the origin must be 0, right? So I'm going to write that here. E origin equals 0. All right, that's what we found in part B. If the electric field is 0, that means that the force is 0, right? Because the force and electric field are related simply by multiplying by the magnitude of the charge that feels the force, in this case, negative Q. So that tells us that the force that charge negative Q feels at the origin is 0. We have that point right there. The next thing we note is that the fact that all these charges are repulsive means that whatever direction the charges are, the force points the opposite way. So if we're on the positive side of the origin, the charges are on the left, so the force must point to the right in the conventionally positive direction. So this one we haven't got a number for yet, but I'm going to sketch that it has to be somewhere up here. Right? We have to have a positive force. If we had a negative force, then that would be like an attractive force. That's clearly not right. Similarly, if we're on the negative side, the force has to push us more sort of back towards the negative side because it wants to repel. So it's going to be somewhere down here. Okay? Now, the next thing to note is that, remember, the force depends on the distance you are from the charges. So the farther you are, the smaller the magnitude of the force has to be. So as x gets really, really big, then this force has to go kind of like to 0, but on the positive side, right, because we can't have a negative, we wouldn't pull it back. And similarly, on the negative side, the force that it feels initially when we start off is going to be very, very small, but it's going to be repulsive, so it's going to be on like almost 0, but on the negative side. So let me move that a little bit. So something actually a little bit more. So kind of like there. So now we know a lot of stuff. We know what a couple points and sort of how it behaves at the ends. We know what sort of sides it has to be on. And this right here would get you 2 points out of the 3 for this question if you just kind of did anything random in that orange area and connected the 3 things that I've drawn in red. That's 3 points already, or 2 points out of the 3 already. So for the last part, we just have to rely on a little bit of, I don't know, I guess I want to say sort of physics sense, and the fact that it wouldn't be logical if the force had any bizarre discontinuities, if traveling like an infinitesimally small distance meant that the force jumped dramatically. It has to be a nice sort of smooth function. So we start at 0. We know it's not 0 all the way through, so at some point we have to end up like up in this area and down in that area, but we have to get back to 0 again. So on this side we have to do something kind of like that, and on this side we have to do something kind of like that. And that's all it really is. This one is a little bit complicated to explain, again, without details of calculus, but the key is that it has to be a simple function, because it wouldn't make any sense otherwise, and the points that I drew initially I think are pretty straightforward to see. As to why it's not more complicated, perhaps, like for example, why didn't I do anything like this? Well, first of all, we know the force can't go negative, so that one clearly doesn't work because of that. So why didn't I do something like that? Well, you're getting sort of farther away from the charges in a simple way. So it doesn't make sense that the force would get big and then small and then big and then small again, right? There's nothing complicated happening, so it has to be as simple as possible. And so this curve that I drew is the simplest possible thing that fits the 3 requirements that I knew I had to have. We went through 0 here, we got back to 0 on both ends, and we go through this positive area there and this negative area there. And as long as I do that, I'm fine. That'd get the full points.